Hi and welcome to the video. In this video we will cover some topics concerning controllers and control systems. We start by looking at what a controller is in general, then continue by looking at feed-forward control and talk about limitations such an approach can have. We use a simple simulation example to demonstrate. Afterwards we talk about what feedback control is and how we can use it to improve the behavior of our system. We then finish with an outlook on what I want to talk about in the next videos. In the videos up until now, we almost exclusively looked at how to simulate systems using a known predefined input. The only exceptions to this would be the last video with our very crude cruise control. The other videos and the simulations in them had the same characteristics. We used a known input and then simply analyzed how the system would behave over time. In control engineering, we want to influence our system so that something very specific happens. Change a temperature, keep a velocity constant, or avoid oscillation in a system. The example I chose for this video is a change of velocity and then holding the velocity constant over time. Very roughly speaking, there are two different approaches how something like this can be achieved. We have pure feed-forward approaches and feedback approaches. The best result can often be achieved if we combine both methods with each other. Let's now look at both briefly. If we are doing feed-forward, we calculate a required input signal based on the model of our system and then execute the calculated input. We do not check if our system actually behaves like we calculated it, we just assume it does. Depending on what you want to achieve in control, you might be able to take a lot of effects into account when planning your feed-forward control signal. Usually, there will always be some small effect that you do not consider in simulation or planning. Small friction effects, you never know your parameters with 100% certainty, so your masses, air resistance coefficients and so on are different in real life than in simulation, and those lead to a deviation between the planned system output and the actual system output if you were to simply execute a pre-planned input signal. Let's look at a concrete example of this in simulation. Here is what we want to achieve. We start at velocity equal to 0, then want to accelerate until we hit 35 meters per second. Hold this velocity for some time, and then reduce the velocity back down to 25 meters per second and hold that. We can now use our system equations to calculate the required engine power to achieve this, and it looks like this here. If we now execute that, we can see that our system does exactly what it should. However, this is only the case if we know everything in our system with 100% accuracy. We now use the input trajectory we planned from our initial parameter set, adjust the mass and air resistance coefficient of our vehicle in simulation to be slightly different and simulate again. If we execute the same input again, we see that, unsurprisingly, our system no longer behaves as it is supposed to. This is also expected. If there is an uncertainty in our system, we can calculate as much as we want to plan our input beforehand, there will always be some error. To fix this error, we can add feedback. Let's look at this next. As the name suggests, we now add feedback to our system in the form of a measurement to correct and readjust our velocity continuously. The way this is done is in the following way. First, we grab a measurement from our system at this point in time here. Then we compare our measured velocity with our target velocity. Based on the comparison, we calculate a new input for our system, send this input to the engine and hold it constant for a certain period of time. This control loop, grab measurements, process, set output, is repeated on a fixed time interval, our controller cycle time. Since we now add feedback to our system, we can react to our velocity being different to the planned velocity and correct it accordingly. Let's add the third simulation with the controller to see what the effect of it is. Because we have now added a feedback to our system, we are able to continuously adjust our control input, and our velocity can follow the trajectory we set out before, even though we still have the same uncertainty between our planned system and the actual system. But as you can see, if we compare the simulation with pure feed forward to the one with the added controller, our error is a lot smaller, and we managed to pretty much follow our desired target velocity very closely. What you are also able to see is how big the difference between the actually required control input and the pre-planned input is, all coming from our parameter uncertainty. Okay, that was pretty much what I wanted to cover in this one. Next time we are taking a closer look at the controller used and talk about different methods how the adjusting of our input based on the measurements can be done. In particular, I want to cover the PID controller because it is quite versatile. Other than that, thank you very much for watching. Like, comment, share and subscribe to not miss any future videos. Bye for now.